So this is on the, and it depends on how fast they're growing, what their lives are like. So it's a few months. It's not, you couldn't pin it down to like a number of days, but it's on the order of a few months.
Great, thanks. There's kind of a similar question and some side questions in the chat. So if you have time to look at that, Heather, that would be great. And we better move on to the next talk. Thanks again. Next, Derek Mallia is going to talk to us about wildfire smoke forecasting. He's research faculty in the Atmospheric Sciences Department at University of Utah. Go ahead, Derek. We see your slides, but we don't hear you yet. Oh, maybe we're not supposed to hear you yet.
Okay, do you guys hear me now?
There you go.
Okay, sorry, I had myself muted. Okay, yeah, so today I'll be talking about improving wildfire smoke forecasts through the implementation of a Canopy model parameterization. And so I'd also like to take the time just to thank my co-authors. So this work would not have been possible without their help. Okay, so the number of large wildfires has been steadily increasing across North America. And so the image on the right kind of provides kind of a vivid testament of this, where this is showing you the 20 largest California wildfires and so on. And the really kind of striking thing about this image is that when you look at this, or look at the number of these large wildfires, most of them have actually occurred pretty recently, either in the past 10 or so years, but actually even more recently than that. And we're seeing this trend kind of across most of the Western US, across different states. And so, this is partially being driven by the fact that we're seeing, more wildfire activity, which is being driven by increasing temperatures, which is related to climate change, which is ultimately resulting in a longer wildfire season. And so what you can just see here is that, there's a pretty good correlation between the number of wildfires and the fire season length. And ultimately, the consensus here is that this is probably being driven by snow melt timing, where we're seeing increasing temperatures, which is melting out the snowpack earlier, and thus drying out our forests and so on, and thus makes them more combustible during the summertime. And so what is the relationship with wildfire smoke? And so kind of unsurprisingly, if you have more wildfires, you're going to have more wildfire smoke. And so the thought here is that this is going to probably degrade the air quality across the Western US, especially as fires continue to get worse. And so Kai Wilmot's actually done a lot of really interesting work looking at this, where he's looked at the 98th percentile PM2.5 trends across the Western US during the month of August, which is the peak of the wildfire season. And what he's actually seen is that we're seeing pretty large increases in these types of events that are located across the Pacific Northwest and parts of the Intermountain West. And then I also have this kind of really nice GOES satellite image showing you an example of one of these events. So this is actually from 2020, when we had those very large wildfires across California. And so this kind of really just kind of emphasizes the need that we need weather forecast models that can actually predict smoke kind of in a forecast setting. So kind of like how we forecast, a winter storm, flash flooding, things along those lines. We also want to make forecasts for smoke. And so the good news is our weather models are now getting, we have the computational resources to actually run at the scales needed to kind of both simulate fires for both research and forecasting applications. And so one such type of model that we'll be using for these kind of smoke forecasts is what we refer to as the coupled fire atmosphere approach, where we have a weather forecast model that is driving our fire spread. And so the fire spread, or the fire within the model, is actually going to be dynamically coupled with the atmosphere. And so what I mean by that is the fire is actually going to be interacting with the atmosphere. And so an example of that would be the wildfire plume rise, where you get this kind of buoyant smoke plume as a result of the heat being generated by the fire. And then what this does is this kind of vertically distributes smoke into the atmosphere. But then at the same time, just due to mass conservation, what happens is your near surface winds near the fire line then start accelerating. And what this can actually do is this can actually accelerate your fire growth. And then you can imagine how this is linked to smoke, such that if your fire is accelerating, it's going to be burning more area, and then thus you'll have more smoke as a result. And so the type of model that the model that we'll be using to kind of carry out this simulations is what we referred to as the weather research and forecast model, coupled with a fire spread model, which we refer to as S-Fire. And so ultimately, this is just the weather research and forecast model, or WRF, that is just dynamically coupled with a fire spread model. But before we can actually run this model, we do have to pre-process some data. For example, we need to get boundary conditions from our global weather models. We also need to get satellite data that can actually characterize the vegetation that we're burning. We also need to be able to characterize the moisture within that vegetation. So we also need to kind of assimilate surface dead fuel moisture observations. And then finally, we also need to be able to initialize the fire location. And so this can either be due through satellite detections or infrared fire perimeters. And so this all gets assimilated with the WRF preprocessing system, or WPS. And then at that point, we can then run our forecast model. And so then we start running our forecast model, and then the fire spread model is then being driven by the meteorology that's being produced by the weather forecast model. That smoke then gets injected into the atmosphere and then ejected around by the wind circulations that you have in your area of interest. And so you can kind of see that here. This is just a number of large wildfires across Northern California back in 2015. And so to kind of look more at this modeling framework, we actually looked at the Pole Creek fire from back in 2018. So this was a fire that was actually two fires, technically speaking. It was actually the Pole Creek and Bald Mountain fire. But this burned near Spanish Fork Canyon back in 2018. And this is one of our largest wildfires during that fire season. And then we were actually running operational WRF fire forecasts during this time. And so fires are ultimately, this is the multi-scale problem. So because of that, we kind of employ this kind of multi-scale kind of model setup where we have a very kind of fine scale kind of simulation that's kind of driving the fire growth and so on. And then what we do is we gradually downscale, or I guess, yeah, downscale or coarsen the resolution, just due to the fact that we're kind of resolving coarser and coarser scale kind of circulations further and further from the fire. And so, you can imagine this kind of larger kind of domain that covers an area larger area across northern Utah is then responsible for transporting the smoke around. And so one reason why this kind of case study was kind of ideal is that we had a number of PM2.5 observations across northern Utah. We have the traction measurements from Logan Mitchell's kind of tracks measurements, and then we also have purple air and our air quality sensors scattered across northern Utah. And then we also, of course, have the DAQ stations as well for looking at PM2.5. And so this kind of allows us, or really gives good spatial representation of what the smoke gradients or the smoke plume looks like as it's being ejected across northern Utah. And so this is just kind of a snapshot showing you the smoke simulation combined with these air quality observations. And so ultimately what you can see here is the smoke is kind of during the nighttime is being ejected down through Spanish Fork Canyon, up through Utah Valley, and then into the Salt Lake Valley, and then eventually being ejected out to the Great Salt Lake. And then these little dots are just showing you the air quality measurements. And ultimately we can see is the model does a pretty reasonable job capturing these smoke plume gradients. And this is pretty impressive since we did actually run this operationally. And so just to kind of summarize this event, basically what happened is during the nighttime, according to our air quality stations located throughout the Salt Lake Valley, during the nighttime, we had this kind of really large kind of increase in PM2.5. And this was kind of being driven by drainage flow, carrying the smoke from Utah Valley and Spanish Fork, and then carried this into the lower elevation areas such as the Salt Lake Valley. And so this spiked PM2.5 and so on. And then during the daytime, what happened is we had convective mixing. And so this was able to loft the smoke further up into the atmosphere. And then the southwesterly, or the stronger southwesterly winds were able to carry the smoke or ejected off into the northeast. And so that was actually driving the smoke away from the Salt Lake City. And so as a result, you saw kind of lower PM2.5 concentrations during the afternoon and the following day. And so ultimately, these simulations actually did a really good job kind of capturing the timing and the shape of the smoke plume. But one problem that we noticed is that our smoke concentrations were still being overestimated by the model. And so these panels here are showing you kind of the observed PM2.5 concentrations and the modeled PM2.5 concentrations. And what you can see here is we're overestimating smoke by roughly a factor of 2 in our forecast model simulations. And then when we started looking at this more thoroughly, what we noticed is our fire growth within our forecast model was actually being overpredicted, especially for the Bald Mountain fire, which actually was burning into parts of Spanish Fork Canyon and Utah Valley. And so part of this is probably going to be due to the fact that we're not capturing fire suppression. But another element of this too is probably, there's some other kind of process that we're not properly depicting with our fire spread model. And so as a result, we kind of had to step back and reevaluate, how we're forecasting things, especially near the fire line, since we have this kind of over prediction in fire growth. And one thing that we kind of noticed is that we thought that we were maybe perhaps over predicting near surface winds right at the fire front. And so ultimately, if you're mispredicting your surface wind speeds, you're going to be misrepresenting the overall fire growth. But unfortunately, with these kind of wildfires, these wildfires occur kind of in data sparse areas. And so it's really difficult to kind of evaluate what's exactly going on. And so we kind of had to step back and kind of look at a kind of a prescribed burn to kind of investigate further what's going on. And so prescribed burns, there's usually a lot more observations. And so one that we looked at was actually based out of Florida back in 2012, where there was a number of wind measurements made right along the fire line, along with smoke measurements downwind of that fire. And so to kind of better depict winds, we actually tried implementing a 1D canopy model parameterization to basically better reproduce winds within a forest canopy. And so we use this kind of 1D canopy model. And then basically using this canopy model, we have this kind of lookup table that makes assumptions about the leaf area index, tree types, and et cetera. The downside of this kind of parameterization is, at least this parameterization that we were using does not actually account for non-local effects. And so this is strictly just, basically estimating the winds within the column. And so the good news is, well, before I jump to that, the first thing that we looked at was, first off, and before we even implement this kind of canopy model parameterization, were we overestimating the winds above the canopy? And overall, our meteorological model did a pretty good job resolving the winds above the canopy. But what we noticed is that consistently we're kind of underestimating or overestimating the winds within the forest canopy, especially for stations that were kind of located within the burn plot. And so when we implemented this kind of canopy model parameterization, what we saw this kind of gradual improvement or this reduction in this bias that we were seeing. And so ultimately, this kind of translated to kind of more realistic fire growth. And so what we saw here is, before we implemented this canopy model parameterization, we had this kind of over prediction of fire growth where the fire was burning too fast and basically it was too hot. And so basically you were kind of burning out this fire too quickly within this kind of burn plot. But when we implemented this canopy model parameterization, this essentially slowed down the fire propagation because we had slower winds, or winds that were more realistically being depicted along the fire line. And so because of that, the fire growth matched more closely to that of the observations. And then when you look at the heat fluxes, what you can kind of see here is that the heat fluxes match that of the observations when we use the canopy model versus when we don't kind of use this canopy model. And then ultimately, this kind of impacts your vertical smoke dispersion or your plume rise, where before we weren't using the canopy model parameterization, we were getting a lot more smoke being produced by the fire. We were also getting the smoke plume that was actually getting lofted really high, much higher than that of the aircraft observed kind of plume tops. And then finally, we had really high kind of vertical velocities as well. But in the simulation where we had the canopy model parameterization, you had a plume rise that actually more closely resembled that of what we were seeing in the aircraft observations of smoke. We also saw a smoke plume that had kind of weaker vertical velocities, and that's ultimately going to be tied to the fact that the fire is releasing less heat, and so because it's releasing less heat, there's going to be less buoyancy within the plume as a result. And then when we actually compare this to downwind smoke measurements, before we actually, when we were looking at the observations, you saw kind of well, we had 3 simulations. We had the constrained, the default simulation and the Canopy simulation. So the one I really just want you to focus on here is the default simulation, which had no Canopy model. And then we had a simulation with the Canopy model. And so what you can see here is the number of matches that we had before we implemented the Canopy model was around 15. But after we implemented the Canopy model, we had smoke simulations that more closely resembled that of what we saw by the aircraft measurements. And so what this is kind of indicating is that implementing this kind of Canopy model, which kind of focuses on the kind of the tree scale, ultimately results in this kind of larger scale improvement of the overall kind of smoke dispersion, which is kind of at this kind of larger scale.
5 minutes.
And so what's next? And so, there's clear linkages between degraded air quality and large wildfires. But, one thing that we want to look at with now this kind of improved kind of smoke model is, how are larger wildfires going to be impacting the wildfire plume rise? And how will this kind of impact the kind of dispersion of smoke going into the future? Another thing that we kind of want to investigate with this research, which was recently funded by DAQ, is, how does wildfire smoke plumes interact with urban emissions? Kind of doing this through kind of a measurement kind of based study is kind of difficult. And so we're hoping to utilize this kind of WRF fire modeling framework to kind of really dig into how certain or different types of urban emissions could actually be impacting photochemistry within the wildfire smoke plume. And then ultimately a bigger question is, how can we add this Canopy model to kind of operational WRF fire simulations? And so the good news is the Landfire satellite product actually includes or incorporates information on tree types, canopy heights, and so on. And so we can actually kind of, add this information into our model to kind of better resolve, canopy model wins and ultimately, hopefully, improve the prediction of smoke forecasts. And so that's all I have for today. And I'd like to thank NSF and the Utah Division of Air Quality for funding this work.
Thanks a lot, Derek. Who has questions?
Hi, Derek. I've got a question. Do you envision this being a tool that could be a daily operational product available every day during wildfire season?
Yeah, so that's the goal of this. A lot of this is also being funded by NASA, and so there is an operational component to this. We're actually running this in real time across California, and we actually applied this to the California's fire season from last year. The last fire season was actually tricky though, because we had a lot of issues with the fires were just much larger than what we're used to dealing with. And so that kind of posed a lot of issues in terms of running this model operationally, especially with memory issues. So we learned a lot from that. But yeah, so we are running this operationally, and we were actually doing it for those California fires from last year. And so the hope here is that with this new canopy parameterization, one thing that we saw with our simulations is that there's a lot of cases where we're over predicting fire growth. And so our hope is that this fire season, we can actually get this into the latest version of Wildfire, and then we can kind of use this operationally and see, does this actually improve our wildfire growth forecasts, over the span of an entire fire season. So that's kind of the goal of this work, or one of the goals of this work.
There's a question in the chat. It says, what would be the limits spatially and temporally on the WRF S-Fire forecasting application, as in how long can it forecast? And then they also ask about the 444 meter domain. That seems to be expensive. Does this lead to a limitation of a smaller domain that could miss the long range transport of big wildfire plumes? So that's two questions in one there.
Yeah, so with the computational resources to stay, we're actually not limited, or we're not as limited by running this at 400 meter resolution. And so we were running these simulations operationally on like 200 to 300 cores, and that's actually pretty easy to do these days. And so we have some funding through NASA to actually pay for those computational resources, but on some of the supercomputers, that's not really much of a problem these days. The 400 meter resolution domain is limited in size. And so what we do there is strategically, we have that domain centered over the fire because we care about those kind of fine scale winds near the mountains just for the fire line. But because of this kind of nested domain setup, what happens is, even though we have this really kind of fine scale domain located over the fire, the smoke, there is two-way coupling between the outermost domains. And so ultimately what's going on is as we get further from the fire, where the smoke gets kind of spread out more, those kind of really fine scale circulations don't matter as much. But we're still kind of capturing in these outer domains the kind of overall transport. For example, in our simulation for the 1.2 kilometer domain, which kind of covered most of northern Utah, that's 1.2 kilometer resolution. It's pretty good for capturing smoke transport across complex terrain. So yeah, I don't think we're super limited, or at least today we aren't. Maybe a couple of years ago it was more of a problem.